Hello students, welcome you all. In mass spectrometry series, today I will explain the general fragmentation methods in molecular ion. So in my previous lecture already I have discussed the alpha cleavage, which is called as the homolytic cleavage, then inductive cleavage or heterolytic cleavage, and also the McLafferty rearrangement and McLafferty +1 rearrangement. Now in this lecture I will explain some other fragmentation methods, for example ortho rearrangement, fragmentation by ortho rearrangement, which is also called as the ortho effect. Then I will discuss the fragmentation by retro-Diel reaction, then this beta-cleavage, allylic cleavage, and removal of water molecules. So these different fragmentation methods that I am going to cover in this lecture. Now, one of the this important fragmentation method is the ortho rearrangement or ortho effect. So this ortho effect, which is also called as the ortho rearrangement. So this here, in some molecules the fragmentation takes place by ortho rearrangement. So one of the main conditions which is required for this ortho rearrangement is the presence of ortho hydrogen in aromatic compounds. So the condition is presence of ortho hydrogen. And such type of rearrangement, it occurs in some ortho substituted aromatic acids, esters, and amide. So if we have ortho substituted aromatic acid, aromatic ester, aromatic amide, then the ortho rearrangement can take place. Okay. So next one, the driving force here. What is the driving force for this is such ortho rearrangement? The driving force is the formation of 6-membered transition state. And also the removal of some small molecules, for example water, alcohol, ammonia. So during rearrangement these molecules will be removed. Now, for example, if we take the general reaction, then if we have, suppose, ortho substituted we may have ortho substituted aromatic acid, ester, and or amide. So here, if we have acid, then this Z, this will be equal to OH. If we have ester, then it may be OR. If we have amide, then this Z, that is NH2, and it would be amide. And this is the ortho position. This is ortho position here. This Y may be this either O, or it may be CH2, or it may be here either it may be NH. This is the Y. So this removal of during the rearrangement, the removal of these molecules will take place, and let us see this how the ortho rearrangement takes place. Now, so this is our molecule. So first of all, what we do, the molecule is converted into the gas form and this means it is vaporized in a mass spectrometer, and then it is ionized at 10 to 15 electron volt. Suppose if it ionizes, then one of the electron removes, and the most loosely held electron removes from here. So here, this is the two. We have these two lone pair of electron on the oxygen atom, and one of the electron which is the most loosely held electron, which can be removed like this. So this is the molecular ion. So this is the molecular ion, or we may represent this molecular ion in this way, this one, or sometimes like this. I have told you, in this way we can represent this molecular ion. Now in ortho effect, the removal of these molecules should take place. So how? So first of all, this bond means here you can see, suppose it is OH and this is H, so H2 that would be removed. In the same way, suppose it is OR and here this H, so ROH that would be removed, and like a NH3 that can be removed. So this will go over here, and this bond over here, and this. So you may see that a bond breaking, bond formation, and there is a ultimate there is a 6-member transition state formation that will take place over here, this 6-member transition state. So what we may write, these are the two double bonds. Now this is converted into single bond, and here we have the double bond. This is Y, and this bond is also broken. Now this one also, this bond is converted into the double bond. This is carbon atom, and this is our oxygen atom like this, and we may show in this way. Okay, so this would be formed. So this radical cation is formed that will be analyzed, or that would be detected by the mass analyzer. So this is the by which the removal takes place, and this is our ortho rearrangement reaction. Now next one is the retro-Diel-Seder reaction. Now let us see the retro-Diel-Seder rearrangement or retro-Diel-Seder reaction, the fragmentation by retro-Diel-Seder reaction. Now all we know that this is reverse of Diel-Seder reaction, and we know that in Diel-Seder reaction we have the diene and dienophile. They combine to give a some cyclic molecule may be formed, like suppose a cycloalkene that will be formed. And in retro-Diel-Seder reaction, what will happen? So if we have cycloalkene, then that will be converted into the diene and dienophile. So mainly such reaction, such type of rearrangement we can see in cycloalkenes. So it is seen in cycloalkenes. So if we have cycloalkenes, then the cleavage is possible by the retro-Diel-Seder reaction. And in such cycloalkenes, if we have a cycloalkenes, then the molecular ion which is formed is it gives a quite intense molecular ion peak. So cycloalkene, why? Because in this rearrangement reaction, the product which is formed and this what I told you, this cycloalkene gives the diene and dienophile, that is reverse retro-Diel-Seder reaction. So when it forms the diene and dienophile, then it requires the cleavage of two carbon-carbon sigma bond, and it's not easy to break two sigma bonds. Okay, so that's why the cleavage is quite it's not easy to cleave this cycloalkene molecule. So that's why the molecular ion and that is for the molecular ion is not easy to fragment. So that's why we get a intense molecular ion peak for cycloalkene. So here for cycloalkene we get intense molecular ion peak. Molecular ion peak. Why? Because it requires the cleavage of two carbon-carbon sigma bonds. Okay. So now suppose if we have a cycloalkene, that is cyclohexene. If we have a cyclohexene, then it will undergo retro-Diel reaction, and the product formed that would be the diene and dienophile. So we may write this means after the removal of one electron, that is from 10 to 15 electron volt, first ionization will take place, and after this ionization means one of the most loosely held electron that will be removed. So this pi electron is the most loosely held electron. So if one of the electron is removed, then positive charge will come and one radical. So this is the radical cation which is formed. Or we can also write this in this form. We may keep double bond as such, and we show it by the radical cation like this. Now, so it will now cleave. You will see this can cleave, and further what will happen? So what I told you, two carbon-carbon bonds will undergo cleavage. So suppose this bond cleaves this bond, okay, and if this comes over here double bond, then this double bond is converted into the single bond, and now this bond will also cleave like this. So what you may see that two bonds undergo cleavage. So this is the one of the bond which is under cleavage, and this is the another bond which cleaves. So two sigma bonds undergo cleavage, and we may get here this single bond is converted into double bond, and this single bond is also converted into double bond. This double bond is converted into this single bond, and we have got this one as a diene and molecular ion. So previously it was molecular ion, still it is the radical cation. Radical cation is present over here. Again, after this cleavage, we are getting the radical cation plus one alkene. Means we are getting the diene and dienophile after the retro-Diel fragmentation reaction. So this is the case. This is one of the cases where the cycloalkene undergo retro-Diel reaction. So in the same way, if you see the another example, suppose if I have now, so this is a well-known natural product, that is limonene. This is limonene, and now first of all, suppose if you want to fragment it, first it will be converted into the molecular ion, and this molecular ion we may show. Suppose here we may show the molecular ion like this, or we may show it. So this double bond most loosely held electron, so this will one electron will be removed from here, or otherwise we may show like this also. And now at 70 electron volt, this at 70 electron volt it would be undergo cleavage. Means two carbon-carbon sigma bond will cleave. So how? So you may see that this bond will move over here. Now this will go over here. Okay. So which bonds have cleaved? So this is one of the bond, and another bond is this is the another bond. These two sigma bond undergo cleavage, and what we may write, this one, okay, and here. So this double bond is converted into single bond. this single bond is converted into double bond, and again this single bond is converted into double bond. This is one of the fragment, and we may show this again in the form of radical cation. And another fragment which is possible, this is the another fragment, okay, and this one. So this is the another fragment. What we have seen, no doubt what I told you, a driving force for this is the formation of 6-member transition state, and this is the 6-member transition state. This bond has broken down and this bond has broken down. Two bonds have broken down to give this fragment, and we will get the peak at some particular m by z value. We will get the peak. So this is about the retro Diel reaction. This is the another method by which the molecule can undergo fragmentation. Now let us see the next one, that is next type of fragmentation is the beta cleavage, which is also called as the inductive cleavage. And you will see such type of cleavage, it occurs in aldehydes and ethers also. You will see such cleavage. Okay, so here the beta bond undergo cleavage. Beta bond undergo cleavage. So suppose if you have aldehyde, and if you have a molecular ion, suppose this is the molecular ion which is formed after the removal of one electron, so it can undergo the beta cleavage. It can also undergo the alpha cleavage that I shown in my previous lecture. Suppose it undergo the alpha cleavage, then what you can see, either this bond breaks or this bond break. So how I show you? I shown you in this way. I shown you alpha cleavage in this way. So the triple bond will get formed with this radical and this radical, and you will have this positive charge, and one of the this is formed over here. This radical will be formed, and this is resonance stabilized. So this was the alpha cleavage. Now suppose if you want to show the beta cleavage, then the bond next to this will undergo cleavage. So this will undergo cleavage, and this cleaves this way. Positive charge will get removed, and you will have the single bond over here, and this radical. Now only radical is left over here, and we have the double bond plus one of the cation, which is the propyl cation is formed. So this is beta cleavage. Now next type is the, suppose let us see the allylic cleavage. Allylic cleavage. Now, so here such type of cleavage, you will see it occurs only in alkyne or alkenes. So when we will see the mass spectra of alkene, then we will discuss this cleavage. So alkene and alkynes. Okay. Now suppose if you have alkene, this is our alkene. So alkene here, and next thing is that the driving force is the formation of allylic carbocation, that you should remember. So what is the driving force for here? Driving force, formation of allylic carbocation. So we should remember. So if alkene is there, then you should see whether we can, after fragmentation, whether we can form some allylic carbocation. If this is possible, then we can show the fragmentation from there. So suppose if you have this alkene. So this is the alkene, and you may see that allylic carbocation is present. This is the allylic carbocation, this is the allylic carbocation. and you may show this one like this. So we may show in this way also. Okay. So now, so how we can cleave so that we get the allylic carbocation? So the possible cleavage is this bond will undergo cleavage. And what you will get, so this radical and radical over here, it will form a double bond, and this one, and positive charge is present over here, plus methyl radical. So you can see that allylic carbocation is formed. So you will get a peak at m minus 15 value, and this m by z value you will get the peak. Okay. Now in the same way, alkyne. In alkyne also you will see. This is alkyne, and this is the radical cation. This is also radical cation, and you may write it in this way again. So this is double bond and positive charge, and this one. So again, if you want to show the allylic cleavage, then it will cleave in this way. So this radical and this radical will form a double bond. This is the double bond which is formed like this. Okay, and this is the, and positive charge is present over here, plus this methyl radical. So as you can see here, we are getting the propargyl cation. So this is called as the propargyl cation. This is what. So this is about the allylic cleavage. Now last type of cleavage which is possible, this is that is the removal of water molecule, and such type of cleavage is possible in case of alcohols. So let us see, if we have a water molecule, that is removal of water molecule. Removal of water molecule. Okay. So it occurs in case of alcohols, or in the same way anthiols. Okay, so dehydration. This is a dehydration reaction. Mainly it is a dehydration reaction, and that's why this alcohol, it shows a very weak molecular ion. This is the reason that the dehydration in alcohol is very much possible. So these alcohols show very weak or absent. It may be absent. They show very weak molecular ion peak. This is the reason. Now suppose if you have an alcohol, this is alcohol, then it can undergo cleavage. So one of the things, that is elimination takes place. That is elimination of water takes place, 1-2 elimination. So if you want to show the 1-2 elimination, then suppose you have a radical cation, and so 1-2 elimination will take place. This is the hydrogen. We have to remove the water molecule. How you can remove the water molecule? So one of this H hydrogen atom that may combine over here, and this will remove. So this will remove with full arrow. We can show it by full arrow. Positive charge is removed, and by this half arrow, this H will combine over here to give you the H2O, and the radical will come over here. Okay, so positive charge is coming at this carbon, and one of the radical is coming over this carbon. So positive charge and this radical. So what we may show is positive charge over here, and radical is present over here. So we may write it in this way. That is, yeah. So this is one of the possibility. Now another possibility, that next type of cleavage is possible. Here this 1-2 elimination And another elimination is also from here also. Suppose this hydrogen is present over here. Then the hydrogen can be removed from here also. Suppose this is the radical cation and this removes the positive charge. Now positive charge will come over here. Now this hydrogen that will be removed and it will combine with this, and radical will come at this carbon. So what you can see, we may see that here, and actually what you saw, at this carbon positive charge is coming and here this radical is coming. Okay, so we may show this radical cation in this way. We may show the radical cation like this. So this is also with the this removal is taking place, this elimination of water molecule is taking place with the formation of cyclic, this transition state of cyclic ion. So these are some general modes of fragmentation. So in general, the molecule or molecular ion can undergo fragmentation in many ways. One is the alpha cleavage or homolytic cleavage, then heterolytic cleavage, which is called as the inductive cleavage, McLafferty rearrangement, McLafferty plus one rearrangement, ortho rearrangement or ortho effect, Diel reaction. Then we saw that is the Betacleavage, and then allylic cleavage, and at the last the removal of water molecule. Thank you.